Today we want to talk about networks. Networks were invented in the 18th century but have become very important in today's modern society. They are used for everything from determining delivery routes on highways that would be most efficient, most inexpensive. They're used to route telephone calls and in particular help with moving messages along the modern internet. The history of networks began in a town called Königsberg. At the time it was in East Prussia, and Leonhard Euler was living there. This town is now known as Kaliningrad in what is now Russia. But anyway, the question came to Euler as he was living there. Someone came to him and said, "Can you cross all 7 bridges?" Here's the bridges of A, B, C, D, E, and F. Can you cross all 7 of these bridges if you go for a walk on a Sunday afternoon without going across the bridges more than one time? So that's really how networking or graph theory began. And in order to talk about that, let's get a little bit of vocabulary. A network is simply a set of points connected by some lines, the points known as vertices or nodes, and the lines known as edges that connect them. What we'll do is we will take the bridge problem and we'll convert it into a model that we call a network model. Okay, so in the diagram of the bridge, the capital letters are the land masses and the small letters are the bridges going across the river. Now you'll notice here on this network model that the same thing happens. See, this dot is this entire land mass up here. D, the dot, is the island here in the river. This dot is the other island, A. B is the other landmass below the river. And then you can see each of the bridges are represented by lowercase letters or these edges, the red edges. Okay? A little bit more network vocabulary. A path is simply following a sequence of edges through a network. Okay? We say a network is connected if every pair of vertices can be joined by some path. An Euler path, this is the one we're most interested in, is a path that traverses each edge once and only once. And again, this comes from the question about the Königsberg Bridge. So we say that a network is traversable if and only if it has an Euler path. So a traversable network and a network that has an Euler path are identical. All right, that's what we're going to be working for. Traversable simply is an English word that means travelable. All right, here's an example of a traversable network, one that has an Euler path. Okay, you should be able to put your pencil on one of the vertices and without lifting your pencil completely trace the figure. Okay, if you have not tried that, stop this video and try it. I will show you one way that that can be done. We could start right here, go up here, up to this one, down here, over here, down here, over here, down there, and then to there. Now you'll notice I did not cross any of those edges twice. Are these networks traversable? Take a look at these two, stop the video, see if you can traverse them, and after you have stopped the video and tried these two, stop the video again with this picture and see if you can get them to, if you can trace all the way around without going over any of the edges twice, but hitting them each once. Okay, you've tried that. What things have you learned from attempting to traverse these networks? Let's take a look at this. You may have discovered the rule. Let's look at the why behind it. Every node or vertex can be designated as odd or even. The vertex is said to be odd if the number of edges connected to it is odd, and it is even if it has an even number of edges connected to it. Let's take a look at an earlier diagram. Here's one that you tried. If you'll notice here, L, the degree of that vertex is 4, M is 4, P is 4, O is 4, and N is 4, because they have 4 edges coming out from each one. Okay? Encountering an even vertex along a path means you have to go through the vertex. So if I'm coming along here, I have to go through the vertex to get 1, 2. So in and out makes 2. Then I can come back and go through in and out again. But notice if it's even and I go in, I've got to come out. Right? Therefore, every even vertex must have as many exits as it has entrances. So if I start on an even vertex, let's just say I start on M, I must finish on that vertex. Here's why. Because if I leave M through this path, okay, let's say then I go around and do something and come into it here and then out here, then I'm going to have to come back into M to finish. My very last thing will be to come into there, and now there's nowhere else to go because I've already gone through all of these paths. So if I start on an even, I've got to end on that even. Okay? Let's take a look at another situation. If a vertex is odd and you begin there, you cannot end up back on that vertex, although you could still pass through as many times as you want. And the vertex where you do end up will also have to be odd. So let's take a look at the one we did here. I started up here at an odd. I left it, okay, went through 4, that was 1 even, through this, there's 2, through this one. So as I came here, now I'm going through 4 again, that upper one, down through here, through that one, and through this one. I'm going to end up on the other odd. So if I start on this odd, I've got to end on that odd. I could start here and end there, but there's no way to start on any of these other even ones and traverse this. In summary, if a network has all even vertices, it is traversable, and you may start at any vertex, but you must end at that same vertex. If a network has exactly 2 odd vertices, it's traversable, but you must start at one of the odd vertices and end at the other one. Any other kind of network is not even traversable. So go back and look at the other examples and see if they agree with what we have just summarized. Can you solve the bridge problem now? There's the network. Is it traversable or not? You should be able to answer it very quickly. Okay, one last thing before we quit today. Is there a relationship between the number of vertices, edges, and regions of a network? Let's investigate. Count the number of vertices, edges, and regions, and be sure to count that unbounded region of this network that we've got here. So let's do that. First, we'll do the regions. There's 1, 2, 3 internal regions and 4 unbounded. The unbounded, of course, is the area outside of all of this. This is region 4 out here. Okay, so we have 4 regions. All right, let's next do the vertices. You'll notice there are 7, count them, they're numbered, and 7 vertices. Okay, and finally we count the edges, and if you'll count those edges, you'll see that there are 9 of them, so we have 9 edges. Is there any kind of relationship between the vertices, regions, and edges of this network or any other network? Well, let's continue our investigation. Down here in the lower right, you see a table. I have created the table and put the numbers that we got on our last network. What I'd like you to do right now is to turn off the video and count the number of vertices, regions, and edges for each of the 3 networks shown. Fill them in the table here, and then look at the pattern to see if you can come up with a relationship. When you have finished, start the video again. Is this what you got for your table? Double check. This should be what you have. Now, what is the relationship? Again, stop the video and see if you can encounter any kind of relationship. There is a formula. Did you come up with it? Here is one way to write it. V plus R is equal to E minus 2, or something similar to that. You could have V plus R minus E is equal to 2, or something else. This is called Euler's formula for networks. He was the one that discovered it, this same Euler that solved the Königsberg bridge problem. Quite interesting. Well, there you have it on networks. In the homework, we'll give you a little bit more information, but that's enough for right now.